Hey student, welcome back. Here we're looking at limits and continuity. And today we're going to be talking about what is a limit? What is limit notation? How can we find a limit by looking at a graph? How can we find a limit by looking at a table? So let's get into it. You may have heard the phrase, the limit as x goes to blank of f of x or of g of x. We often use c in this class, so I wrote the limit as x goes to c of f of x. And if you haven't seen that, we're about to. And the way that we write this with notation would be like so. lim, as x goes towards c, so we write an arrow, x is going towards c, of f of x. So this would mean that take the limit as x goes to c of f of x, exactly. And if this were equal to some number L, we would write it like that. So if we continue, we'll also see today the limit as x goes to c of f of x from the left. We would write this like so, the limit as x goes to c of f of x. And the way that we denote that this is from the left, we're coming from the left, is with a minus, because all of the values that we're going to look at will be less than c. And then when we do it from the right, you may have guessed that this will be a plus, because everything will be above c. Okay, so what is a limit? What is a limit? A limit, so in calculus, in the first video, we talked about how we want to go really close to a point, but we can't go exactly there. If we go exactly to the same point and try to find the slope, we'll be dividing by 0, right? If we try to find the slope with the exact same point, it would be, if this is at 1, and we try to find the slope here, we would be doing whatever f of 1 is minus f of 1 over 1 minus 1. So 0 over 0. So it's really hard for us to do this without a limit. So a limit is a value that we're getting close to without actually being at that value. So if we look at this graph, what we do when we're finding a limit from the graph is we approach from either side. And what I mean by that is here's 1. When we are on the left side of 1 on the x-axis, we kind of watch what's happening to the graph. Like, okay, so we're starting over here. We watch the graph. We're getting close to, it looks like 4. It looks like we're getting close to 4 on the graph. Now, we didn't plug in 1. We're just seeing that these values are getting close to 4. And if we look on the right side, we're coming from the right, so a little bit above 1. And we follow the graph, and we stop before we get to 1. And we see that we're getting close to 4. We might be a little bit above 4. So that's great. The left-sided limit as x goes to 1 from the left of f of x is 4. The limit as x goes to 1 from the right side of f of x is 4. So we did the left side, we did the right side. If these are equal, if and only if these are equal, we say that the limit as x goes to 1 is equal to 4. So if both sides are the same, then that's great. We do have a limit. If they're not the same, our limit does not exist. We'll see that in the future. Okay, so this was from the graph. Now we can look at the table. This table is for this graph. And our strategy here is to pick values that get close to 1 on the left side. So if we look above this line, this would be basically the same thing we did earlier. We did the left-sided limit, the limit as x goes to 1 from the left of f of x. And we notice, okay, we're at 0.9, we're at 3.81. We go to 0.99, we're getting closer to 1. We're at 3.98. We've gotten closer to 4. I don't know if I'm going to 4, maybe I'm going to 4.1, I don't know yet. Then we plug in 0.999, okay, we're getting really close to 4. This is 3.998. We could keep going when you're starting this class. It's a good idea to plug in more and more 9s just so you feel more confident that this is in fact 4. And then we do the same thing on the right side. So I used green for this earlier. We'll say the limit as x goes to 1 from the right of f of x. And I kind of like these to meet in the middle, but really you'd probably plug in 1.1 first and see what value that is. So 4.21, 1.01, and this is a common mistake students make is they'll plug in 1.11. We like the zeros here because this is making it closer. 1.11 would actually be further away. So 1.01 is 4.02. Okay, we're getting closer to 4. 1.001, 4.002, we're getting closer to 4. This is great. This is great. So even without plugging in our value, we see that as we come from the left side, as we come from the right side, our limit is equal to 4. Okay, so that was a good example. Let's look at something that may be a little bit more complicated. Okay, so here we've got an interesting graph, and we'll do the same thing. I'll use red and green for the rest of these. So as we come from the left side, the limit as x goes to 1 from the left of f of x is equal to, okay, on the left side, here we're at about -3. Keep going further, more negative, and then we're off the page. We're going very, very far down. And I think from pre-cal, you all can recognize like what this is between these two values. It looks like we have an asymptote, a vertical asymptote. And so as we come from the left side, this is actually going to be negative infinity is going to be our limit, just based upon what I'm seeing in the graph. Our values keep decreasing. And on the right side, the limit as x goes to 1 from the right, f of x, where we check, okay, there's our value as we get closer. These values just keep getting bigger and getting bigger faster. So we notice that the limit on the right side is equal to infinity. Okay, so what I just said earlier is if these two-sided limits are equal, our limit is whatever that value is. So because these two limits are unequal, the limit as x goes to 1, f of x, we call this DNE. You might remember from the movie Mean Girls, the limit does not exist. Or maybe you're too young for that, I don't know. But we do not have a limit at this point. And we use the expression does not exist, or DNE. Okay, look at the same thing with the table. We're getting closer from the left, 0.9, 0.999, 0.99, 0.999. And we're going from -9 to -99 to -999. And you can see the pattern here. We're just going to be getting larger and more negative. So we can see that the limit from the left, and I know I've already written it, but just so that we say we're doing it from the table too, it's negative infinity. And on the right side, you see we're at 11, then 101, then 1001. So we are getting bigger faster. We're going to infinity here. Okay, so we did not have a limit on the second one. Let's look at the third. Okay, so the left-sided limit as we go towards 1, it looks like if I follow this graph, it looks like we're going towards 0. So I'm going to say the limit as x goes to 1 from the left of f of x. And I'm calling all of these f of x, but we could go with g, with h, whatever. The limit is 0. Okay, now if we look from the right, it's kind of hard to tell. It's a little less than 1, and we'll look at the table later and we'll get a good read on that. But we do know that these are not the same. This is about, let's say, 0.8. Because these two-sided limits are unequal, our limit does not exist. Just so you know, this is pretty much the only time we're going to see something like this, where it's like a broken graph, is with piecewise functions. And I'll show you what that looks like. In this example, I believe it was ln x. from 0, x is greater than or equal to 0 to x is less than 1. And I think this was sine of x for x, not 0, x is greater than or equal to 1. So this is what's called a piecewise function, where we're given two different distinct parts of our function, which are only true for that domain. So when x is between 0 and 1, we're going to plug x's into ln x. And then as soon as x hits the value of 1, we plug it into sine of x. And that's how we get this kind of strange broken shape. Okay, and let's just remember to say that the limit as x goes to 1 of f of x equals d and e. It does not exist. And we can see this again in the table. I might not write it again, but as we're coming from the left, we're getting closer to 0, negative 0.1, negative 0.01, negative 0.001. We're getting close to 0. And then as we come from the right side, we're getting closer to maybe 0.84, whatever sine of 1 is. And these are not equal. So this is a function without a limit at x equals 1. Okay, the last one I want to look at. As we come from the left side, I know you can't really see this, but this is also a 1. So the limit as x goes to 1 from the left of f of x is 1. And if we follow from the right side, the limit as x goes to 1 from the right of f of x is also 1. So because these two values are the same, when going with purple, the limit as x goes to 1 of f of x is 1. Okay, you know, nothing earth-shattering here, but there is something strange about this graph. There's a little gap here. And you may have heard of this. We call it a hole in pre-cal, and we do in calculus as well, but we also call this a removable discontinuity, which we'll talk more about later. But that's what's going on here, discontinuity. Okay, so we don't have a value at 1, but we do have a limit. It doesn't matter what's happening at 1 exactly. It just matters that from the left side, we're going towards, in this case, 1. And on the right side, we're going towards 1 as well. And because those limits are equal, our limit is 1. Now, if we look at our table, we see the same thing. On the left side, we're going towards 1. On the right side, we're going towards 1. But at 1, we don't have a value. That's okay. We're going to talk about what this means because it does mean something for us when we don't have a value there, but it doesn't affect our limit. I'm going to go ahead and just write again, the limit as x goes to 1 of f of x is equal to 1 in this case. Okay, I hope that helped you figure out how to find a limit from a graph, how to find a limit from a table. Later, we're going to learn algebraic methods for finding limits. Have a good day. Bye.